My name is Mathias Lystbæk, and I'll be presenting our work on spatial gaze markers supporting effective task switching in augmented reality. This work was achieved with my co-authors Ken Pfeuffer, Tobias Langlotz, Emil Grønbæk, and Hans Gellersen. So what is this work about? Imagine you're reading a paper, perhaps for a review, and at some point a colleague suggests taking a break or moving to another task, to which you agree. Upon returning, you might struggle to recall where you left off. The concept here is to visually indicate the exact point where you last focused your attention, guiding you back to your previous position in the text, enabling you to seamlessly continue from there. This functionality extends to more professional applications like assembly, where you have to go grab something and place it in a specific place. The spatial gaze markers serve to remind you precisely where you need to return to. Our work is motivated by the crucial role spatial memory plays in our ability to switch between tasks seamlessly. Whether it's returning from a break, navigating different areas, cooking, or simply going about our day, spatial memory guides us. However, this ability can be disrupted by factors such as similar-looking objects, task complexity, or distractions like colleagues or urgent tasks. Prior research has explored how gaze cues can assist in task switching on screens, but often in a rigid, task-dependent manner, requiring prior knowledge of the specific task setup. In contrast, our approach is designed to be task-agnostic, relying solely on environmental mapping without prior knowledge of the ongoing task or surroundings beyond the mesh mapping of the environment. Our primary related work focuses on gaze marks, as presented by Kern et al. Their study demonstrated the effectiveness of gaze marks in guiding users back to navigation screens in 2D tasks within real-world scenarios, serving as a foundational inspiration for our work. They illustrated that a prominent visualization on a navigation map, as depicted here, effectively guided users back to their intended location. Another relevant area of research is AR auto-picking tasks. In these tasks, users are provided with specific visual cues indicating which regions they need to focus on. For example, they might be directed to pick an item from a designated box and place it somewhere, as shown in these images. While our approach uses similar visualizations, it differs in that our system is entirely task-agnostic. Unlike AR auto-picking, which historically relies on task-dependent visualizations, our method offers flexibility across various tasks and environments. Our concept revolves around recognizing gaze fixations and task switches. In this video, I start with looking at the corner of one box, and my fixations are detected. When I turn my head to the other box, the most recent fixation is remembered, and a spatial gaze marker is spawned at that location. When I return to the previous box, the spatial gaze marker guides my attention to where I last looked. When a fixation is then detected near the spatial gaze marker, it is deleted as it no longer is needed at this point. So our concept works on the basis of tracking fixations, detecting task switches, visualizing fixations on return to the prior task, and removing markers when noticed. In more detail, we use the dispersion threshold algorithm for fixation detection, identifying fixations when the gaze signal remains within 1.5 degrees for at least 250 milliseconds. When the user turns their head from the most recent fixation by approximately 33 degrees, we spawn a spatial gaze marker at its location. While it is initially rendered out of view, it becomes visible when the user returns to the prior area. The spatial gaze marker is rendered as a magenta transparent outline circle. We chose magenta due to its visual salience, transparency to maintain visibility of background elements, and an outline format to avoid complete occlusion of the area of interest. Finally, when a new fixation falls within 1.5 degrees of a spatial gaze marker, it disappears, indicating that its purpose has been fulfilled. To evaluate this concept, we came up with two tasks, namely repair and inspection. The repair task is designed to simulate an immediate repair. That means something sticks out to you and you need to fix it. This also simulates cases where spatial memory is limited. The inspection task is meant to simulate a continuous inspection, where you have to check through parts until you find something that is broken and then repair it. As such, inspection also simulates cases where spatial memory may be more established. Both tasks have the same areas, specifically a work area in front of the user and a tools area behind the user. We ask you to refer to our paper for more details on the task design. From the participant's perspective, the tasks look something like this. In the repair task, the participant is initially shown what post-it to repair. After identifying the type of the broken part, they turn to the tools area and pick up the corresponding tool. Depending on conditions, we introduce a distraction between having found the tools and returning to the work area. In this example, the participant is guided by the spatial gaze markers to show them which post-it they should return to. For the inspection, participants go through the post-its manually trying to find one that is broken. When they find one, they turn to the tools area to pick up the corresponding tool and return to the work area. The inspection task did not include any distractions. Similarly to the repair, the user here is guided by the spatial gaze markers. Compared to a baseline of having no markers, we measured how much time it took for participants to relocalize the correct post-it after having returned from the tools area. In the repair task without distractions, we found that spatial gaze markers achieved a 41% time reduction, while in the repair task with distractions, we found a 52% time reduction. We also measured how many rechecks of post-its that the participants performed during the relocalization. That means how many times did they check the wrong post-it before landing on the correct one. And in the repair task without distractions, we found a 95% reduction in rechecks, while in the repair task with distractions, we found a 77% reduction in rechecks. Additionally, we found lower task load specifically in terms of mental demand, effort, and frustration. In summary, we found spatial gaze markers to be more time efficient, result in fewer rechecks, and cause lower task load on the participants. We believe that spatial gaze markers can aid in a variety of tasks, from industrial operations such as selection, maintenance, and installation, to everyday activities like cooking or managing interruptions. Unlike other systems requiring specific environment calibration, spatial gaze markers can be quickly deployed. For example, in this Lego assembly scenario, one simply puts on the headset, lets the headset track the environment, and it seamlessly begins tracking fixations, guiding you as you return to specific areas. That ends my presentation of our work, Spatial Gaze Markers, supporting effective task switching in augmented reality.